All right, hello everyone. I'm Shantanu Jain, and today I'm going to present our work on an algorithm for decoy-free false discovery rate estimation in cross-linking mass spectrometry-based proteomics. This is a joint work with Isu Peng and Predrag Radivoyak. Understanding protein-protein interactions, understanding protein structure and protein-protein interactions is important to study in the study of molecular biology as well as understanding genetic diseases. Cross-linking mass spectrometry-based proteomics is a high-throughput approach to infer structure and interaction where multiple proteins can be analyzed simultaneously. In comparison to low-throughput approaches such as X-ray crystallography, the approach does not provide an atomic resolution of structure or protein-protein interactions. However, the protein-protein interactions and the structure are understood or inferred in terms of protein fragments or peptide pairs that are in close proximity to each other in the 3D space. Now, being a high-throughput approach, it does not, a lot of the peptide pairs that are obtained from this approach could be incorrect. So typically you would need a stringent error control mechanism. So in this work, we develop a decoy-free error control mechanism based on false discovery rate estimation. Um, just to give you a little bit background, the cross-linking mass spectrometry-based proteomics, the key aspect, the key to cross-linking mass spectrometry-based proteomics is a linker molecule such as DEST, which is about 10 to 15 angstroms in length. And this linker molecule is introduced into a protein sample where it would connect and join amino acid pairs that are in close proximity to each other. Then in the next step, the protein gets digested and it's broken down into peptides. However, the linker molecule stays intact. So this leads to a species of cross-linking peptides. Is my mouse visible there? I don't know. So this leads to a species of cross-linking peptides where a pair of peptides are joined together by a linker molecule. And in addition to there are some linear peptides that are not linked by a linker molecule. An enrichment step is often performed to increase the fraction of the cross-linked peptide molecules. And then these and then these cross-linked peptide molecules are passed through a tandem mass spectrometer, which converts them into an MS2 spectrum. This experimental spectrum is then matched against theoretical cross-linked peptides that are obtained from a target protein database. The candidate space of the peptide pairs is reduced based on the MS1 spectrum. And finally, what you get is you have these candidate peptide pairs that get scored and ranked against an experimental spectrum. So the data obtained from this approach can be represented in this tabular format where in the rows you will have the rows correspond to an experimental spectrum and the columns correspond to peptide pairs from the target database that are the matches for the experimental spectrum. So in the first column is the top match, which contains all the peptide pairs that have the highest score. The second match contains all the peptide pairs that have the second highest score, and so on. Notice that in some cases, for some experimental spectra, you might not have a lot of matches. So for example, the third experimental spectra only has the first match, but it does not have the second and the third match. One thing to notice is that the top match, being the highest scoring match, is the most enriched in the correct peptide pairs. And typically, most of the FDR estimation approach relies solely on the top match to perform error control. So now to understand FDR-based error control, let's go back to the standard setting of peptide search, not the cross-link peptide search. So here I'm showing on the left the score distribution of the top scores. You can see that a large fraction of these scores are low scoring and they are likely going to be incorrect. A small fraction of these scores are high scoring, and so they're likely going to be the correct matches. The goal here is to find a threshold such that most of the peptides that score above that threshold are mostly correct. Or in other words, the proportion of peptides that are incorrect above the threshold or the false discovery rate is small. So for a given threshold, false discovery rate is defined as the number of incorrect matches above a threshold divided by the total number of matches. In spite of the simplicity of this formula, you cannot estimate FDR directly using this formula because the number of incorrect matches is not known. However, if you can infer somehow the distribution of the incorrect matches, then you can estimate the incorrect number of incorrect matches. So to understand this, let's look at, on the right, we look at the score. Again, we look at the score distribution of the top score. However, this time we have deconvoluted it in terms of the incorrect score distribution and the correct score distribution. Now, if you look at the area under the incorrect score distribution, the yellow curve to the above the score threshold, then this area, when multiplied by the number of spectra in your sample, it gives you the number of incorrect matches. And this can be used to estimate your FDR. Now, this approach of directly deconvoluting your top score into the incorrect and the correct components is used by the peptide profit tool. However, it has this limitation that it models the correct score distribution by a very restrictive Gaussian distribution. Another alternate approach for false discovery rate control is the target decoy approach. In this approach, instead of just matching an experimental spectra against the peptides on the target proteins, it is also matched against the peptides in the decoy proteins. Typically, the decoy proteins are obtained by shuffling the target sequences or reversing the target sequences. In a standard target decoy approach, what typically happens is you would concatenate the target database and the decoy database, and then search your experimental spectra against this combined concatenated data set, which is double the size of the target database. Now, as a consequence, your top match could either come from the target set or it could come from the decoy set. All the top matches that are coming from the decoy set, they serve as an approximation, or they serve to infer the distribution of the incorrect matches. And then all you need to do to compute FDR is to use this formula where in the numerator you replace the number of incorrect matches by the number of decoy matches. Now, in spite of the simplicity and the popularity of this approach, it has some limitations. For example, it would double the search time because your concatenated database is double the size of the target database. Theoretically, it can be shown that it overestimates FDR because of an additional competition with the decoy, with the extra decoy peptides that are introduced. There's some work that shows that empirically, in certain cases with high accuracy instrument, the FDR can also be underestimated. Typically, the estimates of the FDR obtained from this approach are unstable, specifically at larger thresholds or lower FDR values, which is the typical use case of these approaches. And in theory, if you look at the formula, it can give you an infinite value, and it could also be non-monotonic as a function of the score. However, these can be corrected with some minor modifications. Now, if you apply the target decoy approach to the cross-linking mass spectrometry pipeline, then the formula for FDR computation is slightly different. And that is because you're not searching single peptides, but you're searching pairs of peptides. So here in the numerator, you have decoy matching spectra, which contain at least one peptide matching to a decoy peptide. And as a correction factor, you have to include a set of decoy matching spectra where both the peptides are coming from decoy. The derivation of this formula is complicated, and we can discuss that later if you have any interest in this. But this entire approach suffers from the same limitations as the standard target decoy approach. However, one point to notice here is that the search time could get even longer. Actually, it can get 4 times because now you're searching peptide pairs rather than a single peptide. And also that the FDR computed from this approach can, in practice, can somehow be negative because you're subtracting a term here. Now, to address some of these limitations, we introduce a new approach for FDR estimation for cross-linking MS. And the central idea here is to exploit the second best match in addition to the top match And the second match we are going to use to infer infer some information about the incorrect distribution. Now, to explain this approach, let's go back to the standard setting of searching the regular peptides or the cross-linked ones. And here on the left, I've shown the score distribution of the top scores as well as the second best scores. And the core idea or the modeling assumption here is that we model both the top score and the second best score as a skew normal mixture with up to 3 components. So the 3 components are the correct distribution component, and then there are 2 incorrect distribution components. The first one is the top scoring incorrect distribution, and the second one is the second best scoring incorrect distribution. Now, your top score could be is a mixture of the correct distribution as well as the top scoring incorrect distribution. Here, WC and WI1 are the fraction of the correct and top scoring incorrect matches. Whereas the second score is a mixture of 3 components, where the second best scoring incorrect match is also included. Now, this can happen when the top scoring match is incorrect. The second scoring match could either be second best incorrect, or it could be correct. So we need to account for the case that the second best match could be a second incorrect. Another point to notice here is that whenever the top score is correct, the second score has to be the top incorrect distribution, which means that the proportion of the correct matches in the top score, which is WC, has to be equal to the proportion of top incorrect matches in the second score. So this leads to this constraints WI1 equal to VI1 equal to WC. Now we could fit this model to our data and estimate the incorrect distribution, which is SN theta I, and that could be used to estimate FDR. Now we choose skew-normal mixtures because skew-normal family of distribution is a generalization of the Gaussian distribution that allows for skewness and mitigates some of the limitations of the peptide profit, in addition to also incorporating the second score, which peptide profit does not do. The skew-normal family is a parametric family with 3 parameters. One is the location parameter mu, the scale parameter omega, and the skewness parameter lambda. Here you can see that for lambda equal to 0, the skew-normal family corresponds to a Gaussian family, whereas for a positive lambda, you get a positive skew, and a negative lambda, you get a negative skew. Skew-normal distributions have been known to model competition. There's a theoretical result which says that a maximum of 2 standard Gaussian distribution is a skew-normal distribution, which makes this family a good family to model competition, as in the case for mass spectrometry data. So now if we apply this approach to the more complex cross-linking mass spectrometry, we need to consider 2 additional components. Because in cross-linking mass spectrometry, you can have a spectrum that could have one peptide that is correctly matched and one peptide that is incorrectly matched. So we need to consider it as a separate component. We can't club it together with the incorrect component. So here I introduce J1 and J2, which is the top scoring partially incorrect distribution, and J2 is the second best scoring partially incorrect distribution. Now your S1 is a mixture of 3 components. It has this top partially incorrect skew-normal distribution, whereas S2 is a mixture of 5 components, where it has additionally the top scoring partially incorrect and the second best scoring partially incorrect. Now, if you were to fit this data to the model, fit this model to the data, then you can derive an EM algorithm for this purpose. However, if you just fit it just in that manner, you might not see results. You might see results which look problematic. So though the overall fit of both the top and the second scores here look correct, however, if you look at how they are deconvoluted, you see that the correct distribution, which is in blue, is all over the entire range of the scores, whereas you would expect it only to be on the right side. And so there's no separation between the correct, incorrect, and the partially correct. And to mitigate this issue, we consider 2 sets of constraints that naturally appear in this problem. So one is the weight constraint, The first weight constraint here is the proportion of correct scores in the top score is less than the proportion of top incorrect scores in the second score plus the proportion of top partially incorrect scores in the second score. Now, to see how this comes, we can look at this table where you see that when the top score is correct, there are two possibilities. The second score has to be top partially incorrect or top incorrect. However, that's not the only way the second score can be J1 and I1. If the top score is J1, then also the second score can be I1. And if the top score is I1, then which means that WC has to be less than VJ1 plus VI1. So similarly, we can derive these 8 constraints. And on the side, we have a modification of these constraints that account for the case that in some cases, you would not see that a second score is observed for some spectra. In addition to those constraints, we also include pairwise density constraints, whose role is to position the component densities in the way we expect them to be. So loosely speaking, what we would expect is the distribution of the correct should be on the right side, and then there should be a distribution of the top partially incorrect, then the second best partially incorrect, and then the top incorrect and the second best incorrect. Now, to make this more precise, we introduce a strict partial order relationship. We say that a density F dominates density G if and only if the mode of F is greater than the mode of G, and to all the points to the right of mode of F, F dominates G, or F is greater than G, whereas to all the points which are on the left of the mode of G, G dominates F, or G is greater than F. So here we also show a counterexample G prime, which even though it is on the left side of F, it is not dominated by F, because if you look at the right tail, then in G prime has a higher value in the right tail compared to F. So we incorporate these constraints by a binary search approach along with the EM algorithm. So every time we are updating to a new parameter, we'll do a binary search between the old and the new parameter to see whether the constraints are satisfied. And that allows us to incorporate these constraints seamlessly. So now we can look at the fit of the final model here. This is for 4 of the pride data sets that we considered in our work. We can see that all the distributions are positioned as expected. They are ordered from the right to left with correct, partially incorrect, and incorrect distributions. Here's a fit for all the data sets that we considered in our work, total 10. And some of the things that you want to observe here is that for at least 3 data sets, this one, the QE, RPA, and PEPLib, we see that the target decoy thresholds of 1% FDR are very similar to the thresholds that we get from our approach. In 8 of these data sets, our approach gets more identifications than target decoy, and in 2 of these, target decoys gets more identifications. However, without ground truth data, which is not available in the space of cross-linked peptides, it's difficult to precisely prove that one is correct over the other. But visualizing the relationship between the top scores and the second score, we feel confident that our approach is working well. Now, we did some study of stability of thresholds, 1% FDR thresholds. We ran bootstrap samples and looked at the box variance in the 1% FDR thresholds. We see that typically the target decoy-based thresholds have more variance compared to which is in the blue box plot, whereas the green box plot corresponds to our approach has lesser variance. However, in this one data set, the target decoy has smaller variance. Next, we consider the search time for comparing how a search with decoy database versus search without decoy database. So the first column shows the search time with decoy database. You can clearly see that it's significantly longer than the search time without decoy database. We also included the model running time, which is in some minutes to run a single iteration of the model. Though in our algorithm, we run 240 iterations of this algorithm, so that brings the time up. However, we believe that there is a lot of scope of improvement or optimizing this algorithm with implementation in C, that it could speed up a lot more. So summarizing, I would say that we derive a decoy-free approach for false discovery rate estimation in cross-linking mass spectrometry-based proteomics. Our experiments show that our approach is more stable than the target decoy approach, and there is significant potential for improving the speed of cross-link MS pipeline search, which could typically run even for days. So I would want to thank my collaborators, Isu and Peja, as well as thank you all of you for your attention. Thank you. Open to questions.
Thank you for the talk. I'm just wondering, what is your motivation to include the second best match when you try to extend the model complexity?
Basically, so if you look at the distribution, the central piece of estimating FDR is to be able to estimate the incorrect score distribution. And as much data, first of all, you can include from the incorrect scores is better. Now, the second scores are going to be predominantly incorrect. So that is one rationale. And also, okay, maybe here is a better example. Yeah. So if you look at the score distribution of incorrects, they tend to be at the lower values. So it kind of nicely, and you also know that in the second scores will contain the top scoring incorrect. So it does contain the information about the top scoring incorrects, and very less number of them are going to be the correct ones. So this kind of helps us to identify what's the good threshold where you to allow to constrain the distribution of the top incorrects using the second incorrects, because it doesn't have a lot of corrects. So there's less chance of getting confused where the corrects are versus where the incorrects are.
Yeah. Allow me elaborate a little bit, because you include two components in one peptide, the best match, second best match. Then in the cross-linking setting, you basically include the three incorrect matches: the correct, incorrect, incorrect, correct,
Right.
and the incorrect, incorrect.
Right.
Which makes your model having like a three incorrect components and plus one top match, which is supposed to
so
be
that's I think every time we build a model, we have to make some trade-offs. Now it can be very easily argued that any score coming from a partially incorrect match on average is going to be much higher than that coming from a completely incorrect match. So modeling them by a same unimodal distribution doesn't seem that it is going to introduce a lot of bias. So we surely need a different distribution for it, because otherwise there's too much bias. Now, it's fair that if we have so many components and there's like model complexity high, and it could lead to issues of identifiability, which we do find. If we look at the score distributions of the model fit, the model fit from when we don't consider any constraints, then we do see that we don't get the kind of fits that we want. We see that the correct distribution and the incorrect distributions are all over the place. Now, what starts making the algorithm work is introducing these constraints, which especially the pairwise density constraints that get them to be get the distributions to be positioned at the right places. And though in theory the model complexity is high, it reduces it in some practice.
Thank you. One last question. When you do the targeted decoy part, did you include the second best match in the targeted decoy or not?
How would we include the second
well,
match?
When you do the targeted decoy,
target decoy, we don't consider the second best match. I mean, that framework does not rely on the second best match at all. It only looks at the top match.
We can talk offline.
Okay, yeah. I would be happy to know if you have some
Thank you.
ideas about it.
Thanks for the great talk. My question goes a little bit into the same direction as the first question. I was wondering, how narrow do you make your isolation window when you acquire your cross-linking MS data? I presume it has to be pretty narrow, because you rely here on the best match and the second best match, but inside of your isolation window, you might not only have one correct peptide pair, but you could have multiple peptide pairs that contribute to your experimental spectrum. So now all of a sudden you not only have one correct peptide pair, but two. So like, how does your model account for that?
So, I mean, we did see sometimes there were two correct peptide pairs, but that was mostly because, uh, where the linking is happening essentially within the peptides. But I don't know how can there be like two correct for a given spectra. How can there be two correct peptide matches?
Because you have isolated multiple peptides and not only a single one for fragmentation. Like that's why I asked about how.
But it is a data dependent acquisition, right? So we typically assume that only a single, like a peptide, only a peptide spectrum for a peptide pair goes at a time.
Yeah, but that's exactly what I'm saying. So even though you do DDA, your DDA spectra will contain multiple precursors that you co-isolate, even though you isolate with, say, 0.4 Thompson on each side of the precursor that you want to target. There might be a second peptide, just 0.2 Thompson next to your targeted peptide that will contaminate your MS2 spectrum with true signal. So the question is, how does your model account for that?
I mean, our model doesn't account for that aspect. I mean, typically I think in most of the approaches for DDA, those things are assumed that it will, like some error might happen, but it won't be like predominantly, like most spectrums will be clean and maybe some spectrums won't be clean.
Yeah, unfortunately, that's not the case. Like 50% of the spectra are actually contaminated with multiple peptides.
Okay. All right.